But now we're alone. So it seems to be working though. So we'll take our victories where we can get them. Okay. Happy afternoon, everybody. Congratulations on surviving your first week. Actually, congratulations to all of us, quite frankly, on surviving our first week. I know it's been frustrating. This class, no less than probably any others, but you guys have been real troopers in putting up with things. So thank you, and you have done an awesome job. Actually, does the light situation kind of not make a lot of sense, does it? Well, does it or worse? Yeah. This is good. Okay, so we're going to pick up where we left off on Wednesday, and so we had left off talking about the different types of questions we can ask in ecology, and then I have a few slides we're going to skim through to get to the interesting things since we've lost so much time on Wednesday. So we wanted to look at the difference between autoecology and population ecology. I think that's about where we left off. What are the types of questions that you can ask about organismal ecology? Where is that going to be focused? All right, well, let's switch the gun, right? Most people are focused and interested on population level ecology. What kinds of things would you ask about that? We defined population well on Wednesday, right? That was all of one species in a given area, so like all of the gray squirrels on campus. So what kinds of questions could you ask about population level ecology?
What evolutionary characteristics make them like more survival more likely?
Okay, so we could ask what kinds of characteristics make the population of gray squirrels more or less survivable for dealing with campus, for example, right? Okay, and that's a pretty common way to deal with it. Okay, so why is this population resistant or susceptible to disease, right, when something comes through? Okay. Why is this population of squirrels less likely to get run over by a car? More likely to attack you for a French fry when the gray squirrels that are up in the Kanawha forest are more likely to avoid you, right? Okay, so anything like that. Okay, so what about organismal? What types of questions would you ask about an organism? The ecology of an organism. Anybody here want to go into medical school or be vets? It's my first class ever. That is great. I do not have to tamper this to that exclusively for once. So those are really common questions that you'd ask there, right? So when organisms get injured or when they have diseases, right, you're looking at just a single organism, right, that has gotten sick or has gotten injured, okay, and how their body is coping with that. Okay, rehab centers deal with that a lot. Have a single organism, okay, and how it's coping to an environmental or a stressful situation. Okay. We are actually going to end up coming back to this anyway when we look at dispersal, so this is one of the slides we're going to skip. So let's look at community. So what is the difference between community and population? Population is one specific species in an area, good, and community is everything. Okay, now when we say everything in an area, we mean biotic or living specifically, right? And we want to be careful with our mammal bias. We tend to think of all living things to be all animals, right? And particularly if we've been through zoo more recently than botany, it's a little easier even to do that. So this does include plants as well. Right, so again, if we're thinking about our campus population, we have the gray squirrels, and we have the people, and we have the 13-striped gophers, and we have the maple trees, and the oak trees, and the grass. And I am not any good at plants, so there are probably many that I am embarrassing myself by ignoring, but the many species of plants that are hanging out here, and all of the insects, which we also have a tendency to forget, are living, breathing organisms, right? So all of the lunar moths and the obnoxious sugar ants and all of those organisms are included here as well. Okay. So it also include things like bacteria and fungi if you wanted, right? And so the depth here sometimes depends on your question, right? You don't always have to include everything in the trophic system, okay? But these things do count, right? Remember, living things are single cell and not. All right. Okay, and then usually, despite the fact we know there's a biosphere level, in ecology we usually stop at ecosystem level. Okay, so remember the key here at the ecosystem level, with all of these, right, these are additive. We went from one individual to many individuals, all of the same species. Then we went to many different species, all living, okay? And now we have our many species of living things, and now we have non-living things in addition to. Okay, so we have the biotic and our abiotic added in here. Okay. So we want to think about this might be soil, or anything that includes the non-living habitat for our organisms. This might also include weather, right, all of our listed abiotic components from before, as well as all the things we talked about before too, nutrients, pH, and all of that business from Wednesday. Okay, and again, this can get as big or as small as your questions are. Okay, but anytime that you're going to include an abiotic component, you're usually thinking ecosystem level. I'm just going to pop and check. Collaborate. Because it has stopped recording on me 3 times today. So, all right. Sorry about that, guys. Okay. Any questions that feel good? Okay, pretty intuitive. That's angry. It's so angry. Okay, so if we have some clarifying examples, right? So a question you might ask about community could be how migrating birds, right, so that's one species, would affect the local berry populations. That's another species. So we have two living species interacting together. All right, so that's community. And this could have many living species. I'm a simple creature at heart. Something tangible and testable. Okay, if you're asking ecosystem level question, you might ask how fertilizer runoff is affecting growth in a pond community. All right, so here's the key. Your pond community could be any level of things. Okay, so maybe we're talking about fishes, so trout or guppies. Maybe we're talking about zooplankton. We might even be talking about birds like gulls that are feeding. Live your best life, right? Okay, but so our community could be several different living species. Okay, but here, right, we have nitrogen, phosphorus, maybe some calcium. So clear non-living components that are being added in here. Okay, so we have direct or indirect effect of these non-living components on a living component. JP.
So if that wasn't a fertilizer and it wasn't abiotic and it was biotic, would that make the community?
Correct. So if this was also a living thing, okay, so then this would switch over to a community level. Okay, so in this case, it's really important that the way you couch your question is very clear. So if you want to be asking an ecosystem level question, you want to make sure that in your question and in your hypothesis that you're clearly showing that you're including some sort of abiotic component. It's a good question. Okay, so any question, for example, that is including climate change, is going to be an ecosystem level question, right? Because climate change has, by its very nature, abiotic components, right? Because it's including these drought or biome level components, right? Long-term temperature, long-term weather patterns, okay? And all of that is non-living. And then ultimately their effect on one or more species. Does that make sense? Okay, any questions about any of that? I'm just going to be real weird about this. I understand. Okay, so we're going to go and talk through some of the climate, and this will be climate light, because I want to get through about as much of this as possible. It's my least favorite unit anyway. I like talking about climate, but of all the cool stuff we talk through, it's probably my least favorite thing anyway. So we got to trim somewhere. It's fine. So I'm going to introduce climate. Some of these early slides, I'm not going to trim them, but I'm going to trim down how much I talk about them. So we're going to go light on the details. Probably is not going to make anyone in here cry. And then when we get into these ecological distribution models, particularly in the marine, that's where I'm going to cut some of them. So we're going to cut things like the thermohaline circulation, which is interesting. But ultimately, for the kinds of things we'll talk about in class, there's going to be less direct effect on the types of things we talk about. So it makes the most sense to cut those. If you guys are interested about them, though, I'm happy to discuss them later or online. Okay? Does that seem fair? Okay. So let's introduce climate. Now, one of the main things I want to talk about is, most of the time I don't see students mix these up, but this is a really common issue. And it's one of those like chair flipper issues when you're talking to someone who's really stubborn on why climate change is fake, is that climate and weather are ultimately not the same thing, right? So the fact that we have a really cold day in the middle of winter, right? Or normal weather patterns for a short period of time does not mean climate change isn't occurring. And the main difference for that, of course, is because weather and climate are not the same, right? So weather is what you feel every day when you sign on to your phone apps and it tells you what the day is going to be like and is ultimately horrifically wrong, and so you're wearing the wrong clothes and forget your umbrella. That is weather. It's horrendously difficult to predict, okay, but is current. And that's the real key. So when you say it's 86 degrees, there is 92% humidity, and it is or is going to rain in the next 10 hours, okay, that is weather. Okay, really anything that you're doing in a 5-day forecast kind of business, that's all weather. Okay? Climate is different because we're talking long term. And we're talking broader than a year type business. A real forecast and hindcasting, where you can say it is significantly hotter than it was last year. Okay? Or when you get the weatherman saying, this is the hottest day on record since 1905. Okay? That is a climate pattern. Okay? And also horrendously disconcerting. Okay? When you have fishermen say, this part of the Gulf used to freeze, so I could walk out on it and throw out lobster traps, and now it doesn't anymore. That is climate. Okay? So when you're saying a pattern, okay, so really tangible examples of this are when you're saying summer averages. Okay, so living down here now, it's like 90 in the summer. Okay, I grew up in Minnesota and did my schooling up in Maine. It did not get like 90 in humid where I come from. This has been a learning experience. So the hottest day of the year where I come from is like 83. So I bought shorts to live here. So the difference in averages is pretty significant. And 10 degrees doesn't seem like a big deal. It super is a really big deal. Breaking 100 is a super big deal. So those types of averages, okay, things like El Nino, La Nina, okay, those are these broad scale warmth and moisture movements, okay. We're going to talk about biome distinctions, okay, at the end here. So when you say something like, I lived in Maine, right, and so that is the taiga, right, so an area that has that sort of borderline permafrosty kind of area. We all know what a tropical area is, right? So you can kind of picture these temperate versus tropical versus Arctic spaces. Even though the daily or even weekly temperature in those areas does fluctuate, you can very distinctly picture the Arctic versus the tropics. Okay? Those biome distinctions are climate. Okay, so climate ends up more important than weather, right? Because while weather is day to day and it affects organisms, organisms care whether it's sunny or rainy, certainly. But since climate is long term, weather will change. We used to have a saying in Maine, if you don't like the weather, wait a minute, right? But climate isn't like that, okay? If you live in an area that has a certain type of climate, okay, we live in West Virginia, if you like a lot of snow, move. Okay, you just don't get that here. I've lived here for 3 years, we've had 3 snow days. I used to get snow up to here as a kid. You're not going to get that here, okay? At least not anymore, as far as I can tell. If you used to get that here, as far as I can tell, that is far over. So you have to go somewhere else. Okay? You're not going to get these sorts of things, at least not for chronic days. We're not going to burrow into the snow standing up, okay? So these sorts of changes are climactic. And so what we're going to do is show climate is important because this is what creates habitat. And if you remember, ultimately, and we talked about this in zoology, niche, right? This creates a core part of an organism's identity within its environment. So its tolerance and preferences in its place and how it fits like a puzzle piece in its environment among other organisms. And so we'll talk a lot about competition and mutualism in our, I think, our third unit in the course, right? And climate kind of sets that up. And of course, climate itself is coming largely from things like the sun. And so we're gonna do climate light and talk about where things like the greenhouse gases come from to set up these larger scale climatic patterns. We are not going to review this too much. Okay, all I care, I'm not going to go into this deeply, is remember that ultimately climatic pieces get reset up from the sun, and we're all talking about conversion or transfer of energy. Okay, I don't necessarily care anymore, okay, that we're memorizing the law of thermodynamics. Does that feel okay? Okay, so that's our big take-home picture from the slide, is energy is taken from the sun, transferred, and converted. Okay, so just like we think about everything else, okay, just like food is converted in glycolysis, energy is converted from the sun, and this creates climate. And we're going to look at some examples on how that is occurring. Wow, that is loud. So as I flip through slides, my goal is not to stress you, right? We're just de-emphasizing them. If you feel stressed, I just need you to holler, okay? Okay, so again, I'm basically going to cut this. So let's look at climate itself. Am I still recording? I'm so stressed about that. Looks like yes. Okay. Okay, so ultimately I was going to talk a lot about the details in here, and we're going to de-emphasize the details, but I really want to look at the patterns when I'm looking at this. So the pattern system on here is what ends up creating our atmosphere overall and the greenhouse gas system, which starts out good, ends up bad, right, which we know. So as we're looking at this, our blue bar, it's like a crayon. We're just gonna, the sun. We're gonna commit. We're gonna commit. Okay, the blue bar is the sun. Right, so this is the vast majority of all of the energy that's coming into the Earth, which is why it gets to 100 again. We're not going to focus on the numbers itself. Okay, so most of the energy coming into the Earth is coming in from the sun. Okay, and so the key here is we look at the general pattern. I need these numbers to not be so big. There we go. The general pattern of the numbers is not all of it makes it to the ground, and at least stays there, right? But about half does. Okay. So then we need to ask ourselves, what is happening to the rest? Okay. And so what's happening to the rest is the cloud layer and the atmosphere layer. Okay. So we get absorption and reflection by this atmospheric cloud layer. Okay. So that's what these other bars are ultimately going to be focused on. Okay. So this red bar section looks super dramatic, like, oh my gosh, we have like 98% there. It's like 98 of this percent, right? So it seems super dramatic, but it's basically saying as the atmosphere absorbs a bunch of that sun's heat, okay, eventually it's also going to, a bunch of that flows down. Okay. So ultimately, what I really want you to take home here, got this broken down on later slides. There we go. right, is the ground is absorbing a large portion of what the sun's giving off. Right, remember, we're not focusing on the percents anymore, so just large chunks. Right, and the atmosphere is getting the other chunk of this. Whether it's the actual atmosphere, remember we're getting different density of air there, and that's what's causing that absorption, or the fluff. And the reason that clouds can reflect light is because they're floofy. Right, the same reason that this stuff can reflect things, it's the same reason clouds can, it's just water glare. So we're getting about half the sun, straight from the sun. Okay, and this is key, right? We wouldn't want 100% of the sun all at once. That's not super great. Okay, so the atmosphere is really protecting us, and so is the water in the clouds. So we're getting a protective layer there. Okay, let's pop over and look at the next biggest bar set. So from that ground, okay, that's all leaving again. Right? This is why the ground feels warm under your feet, particularly at night, right, as the air around you is cooled. So the ground feels warm. We're losing that energy. Okay, now again, most of this is getting caught up by the atmosphere. So as you might imagine, we're going to look at the atmosphere after this very specifically. Okay. The heat itself from the ground, we got a lot from the sun, and we do get a little bit of heat from the ground itself. Humans do a little bit of this, right? We warm the earth with our business, right? Our buildings do this, right? And we get a little bit from the earth's core as well. That's why this number is bigger than 100. Okay, but most of that is still absorbed by the atmosphere, and then we just like lose a little bit. Okay, but again, we see that the atmosphere is doing most of the work. It's not a ton of just like randomly lost crap here. Okay, so most of the energy that comes into the planet stays in the planet. And this is generally, as we're going to find, why we're not all dead. Okay. So here's the key. Of everything that's happened so far, okay, it's come in and either been hitting the ground or trapped in the atmosphere. And when it goes to leave, it's trapped in the atmosphere. So the atmosphere has most of the stuff. Okay, it's basically directing traffic. And it's going to say, go back down to the ground, or ultimately it will release some portion of the heat and energy that it has. Okay, this is where the term greenhouse effect comes from. So you can actually imagine the Earth being all the little plants in an actual greenhouse, like the glass ones that you build. And the atmosphere serves as that glass shield over the top of the plants in the greenhouse. And that's functioning the same way. And that's why the greenhouses are so warm as the sun comes through the glass in the greenhouse, right? It gets trapped inside, which is why greenhouses are so warm. Right? So the greenhouse glass is serving like this atmosphere is serving. It's trapping all that energy and that heat, making it nice and warm in there so the plants don't die. It's warm and moist. The atmosphere is doing the same thing for planet Earth. It's trapping it in there so it's nice and warm so we don't die. Okay, this is at its core good. Okay, it's like lots of not death. Okay, this is how it fundamentally works on a big scale. Okay, I'm a walker. Here's us. Okay, so you have that big solar radiation bar, right, the original 100%, coming down to Earth. Okay, so you can see, okay, that blue and red bar, which is a normal amount of atmosphere gas, okay, trapping that heat and sort of creating that greenhouse gas, right, keeping Earth warm and moist so animals and plants can live on here, not freeze to death, not dry out, and not die. Okay, so this is normal with planets that have atmospheres. Okay, we get life. Okay, so we've always had a greenhouse effect. Now, most of the time when you hear greenhouse gases and greenhouse effect, this is a bad thing, and there's a reason for that. The reason for that is because it's a delicate balance. Would you please just do the thing? Okay. And that's because as we alter the carbon cycle, okay, most greenhouse gases are carbon-based, so there's a lot of carbon naturally in the ecosystem, most of which are cycled, right? So there's normally so much in the atmosphere, and what goes up must come down, right? And it's used by organisms, eat each other, some of it gets trapped, okay? But it's a complete cycle, so the same amount that goes up is the same amount more or less that comes down. What ended up happening and why greenhouse gases is now like a bad word is because humans added big numbers to the up. And there's no down cycle for us, right? We don't have a downswing. This is really loud. Okay, so with everything else, okay, in nature, there's complete cycles. We have up arrows and down arrows. Okay, we have fixers and releasers. But when humans entered the scene, this stopped becoming a balanced cycle. So we release a lot of carbon, which in and of itself would not necessarily be a bad thing, but we don't take down any carbon. And so this is why it's pollution. It's stuff that doesn't belong there that we don't fix. And so the greenhouse gas thing becomes a problem because compared to the old greenhouse effect, it's enhanced. And so we end up with a much thicker atmosphere. Okay. Which means that we end up trapping significantly more of that reflected heat. Okay, so it's like having thicker panes on our greenhouse. Okay, it was always trapping heat, but now it's trapping like a lot of heat. Okay, so let's look at the different, everything about that feel good? Okay, so that's general energy transference. So let's look at ecological distributions within these. We're going to look at some sub-areas. Okay, some of these potentially will feel familiar, depending on what year you took zone. So the first thing we're going to look at is ocean zones. Okay. In class, we're going to spend most of the time looking at the zones with the vast majority of life, which is anything above the abyssal zone, okay, named as you might imagine because abyss. Okay. So well into the dark zone. Okay, but ultimately when we're looking at this, what I really want you to focus on is the different ways we can split this up, right? So as we're looking here, we're really focusing on, you're fine, light. Okay, so at this point we're looking at the loss of light attenuation. Right, so the very top there, we certainly have the photic and aphotic zone. Okay, the aphotic zone isn't necessarily complete loss of light, but it's complete loss of colored light. And so we can't do photosynthesis anymore, which is why this image shows the cutoff of that sort of greenness at the bottom of the photic zone, because we lose pretty much all marine algae at that stage. Okay. In the aphotic zone, you see it's still like a light blue. We do still see some color, even to some degree in the bathypelagic zone. A lot of these are like our reds and purples. And as we know, right, if you have like those kind of like funny galaxy lights or whatever, even when you let those play, they kind of serve as night lights because the colors are very dark, even compared to a blue or a green bulb. If you have those, I recommend playing with them, right? Run a red bulb for a little while and then click it over to like a blue or a green, and it'll kind of like shock your eyes because it'll seem like you turned on a bright light. And it's very surreal. And that's what you're seeing here is the loss as we switch down into the aphotic zone of all of those brighter colors. When we get down into the abyssal zone, there's no light at all ultimately besides some very dark reds. And that's why when you see those videos, excuse me guys, of the animals that have fluorescence, that those are the colors that they tend to use, because those are the only colors that show. The other thing that you want to notice is, as we move this way, we're talking about depth. Okay, and that's the intertidal, the neritic, and the oceanic. Also sometimes called pelagic. And that pelagic zone will pair up with the freshwater. But basically meaning open water. You can stand there and your feet won't touch, right? Okay. The intertidal zone is, of course, just referring to anything that isn't always covered by water. And the neritic zone is somewhere where there's still regular drops of land, but is always going to be covered by water. And so you can imagine as an organism, right, the different types of use of land here. That feel okay? Okay, we're pretty much going to skip all of this ocean current business. It's kind of a pain anyway, so I guess it's not the end of the world. Okay, so let's skip straight down into talking about freshwater. Okay, we're talking about freshwater. Ultimately on Earth, there's two types of freshwater we call lotic and lentic. Lotic is our flowing water, and I mean flowing water that is constantly moving, so think rivers and streams. Okay, so organisms that live in these are looking for the water to be moving constantly. They'll be adapted to water moving constantly, so they may literally even sit in one place and let food come to them with their mouth open, right? So some caddisflies, for example, will stick themselves on a rock, turn themselves toward the flowing water, and just hold their mouths open and let the food come to them, right? So it's an entire different situation than lentic, right? Lentic is going to be still water or relatively still water. So these are going to be our lakes and ponds. Okay, now these may be closed systems, right? A pond that is basically standalone, or an open system, a pond that may have a river or stream on one end or the other. Okay. Now, We can break our ponds and streams into the same sort of setup that we did our marine system. With depth, oops, sorry, got that backwards here. Light and depth. Okay, so here we see that, I mean, we don't have an abyssal zone in a pond, right? It doesn't get that dark, but we do have a photic and aphotic zone most of the time. Okay, so again, the photic zone is going to be the area we can get photosynthesis. Okay, the aphotic zone is going to be non-photosynthetic most of the time. Okay, you may have some ponds that don't even have an aphotic zone. Right, we can kind of imagine those sort of nasty, stagnant, very shallow ponds. Okay, with depth, for the most part, we can call it littoral. The littoral zone is going to be the area along the side where pretty much you don't really go below your knees. Okay, and this is commonly also marked by the fact, if you look on here, okay, we have standing crop of land plants. Okay, so this is not only still in the aphotic zone, but this is so shallow that you can get like those shore weeds. Okay, when we're in the limnetic zone, okay, it's too deep for that. Okay, you will also sometimes see this referred to as the pelagic, okay, or open water. Okay. The benthic zone, and this was also shown on the marine side, but that basically just means you're literally on the sand. So this is anywhere in any water system where you're talking about something that's touching the sand. So if I'm in the ocean, I'm just like a crab crawling across the bottom. And sometimes this can be any depth. Okay, a flounder sitting at the bottom, sitting on the benthos. Okay, the marine, sometimes they get a little fancy. It's the abyssal benthos. Right? It's just the very deep benthic zone. But it's just the benthic zone. Right? Marine people are just a little with their stuff. Still feel good? Oh man, don't blame me. Okay. Now, as we're talking, listen. As we're talking about lentic things, if your water is not naturally flowing on your own, okay, this means that you're not getting what's called mixing pretty regularly, right? So if I'm a flowing, loaded system, right, all my nutrients, all my organisms are constantly moving, they're constantly getting mixed. If I'm in a lentic system, I'm still, which means everything stratifies. And I can see a pretty good example of that here. No, in this picture. Okay, stratification just means layered. Okay. And this actually occurs pretty commonly. You've probably noticed this if you've gone swimming in a pond, how the top feels very warm, and as you slowly lower yourself in, you can feel yourself slowly get colder and colder and colder. Okay, that's just temperature stratification, but it happens with everything in the lake, right? Because it's just not getting mixed up. Okay, so these still freshwater areas only have so many times a year they really get a chance to get mixed up. Okay, and that's with everything. So we just talked about temperature because that feels very visceral. I can feel the temperature. That's nutrients, okay, and oxygen. And this is why this becomes very problematic for some still water areas, because the oxygen can get very trapped in these freshwater systems. And so the top of this is going to get mixed, right, because it's actually going to see air. So diffusion can happen there, right? Or your butts are going to be splashing around in it. Okay, but diffusion is not going to happen in something that's quite deep, right? We know diffusion is very limited on large bodies, which is why you don't diffuse oxygen into your bodies. So at the bottom here, oxygen just doesn't happen. And so we end up with these pockets of anoxic, or without oxygen, areas. Okay. And so this is where you hear tell of lakes or even Gulf coasts, when it gets very, very warm and things get very, very stratified, of fish kills, right, or organisms dying, because the area has become so stratified and so anoxic. Did not take attendance again. Okay, so we're going to start on Monday with turnover, and then the only other thing I'm going to talk about before we move on is the biomes thing, so I have a little bit of an activity. So we'll probably spend the first 10 minutes of class. So we almost completely caught up. Not bad. Like I said, you guys have been absolutely awesome and troopers about all this. I'm so proud of all of you. I appreciate your patience. See, this class recorded the whole time. I don't know.